Hello again, guys. Welcome to lecture 2 of our lecture series, Chemistry for Engineers. Today, we'll be looking at atoms and molecules. In addition to learning more about the periodic table, we will be understanding a few basic concepts in a bit more detail, such as the atom, isotopes, molecules, monomers, polymers, ions, and compounds. So we know from the last lecture that the atom is the building block of matter. Traditionally, it's known as the smallest particle to exist, but we know that you also have subatomic particles that are smaller than the atom itself. The atom consists of proton, neutron, and electron. It has a central nucleus. The nucleus consists of a proton, which is positively charged, a neutron, which is neutral. We will also look at the fact that the proton basically constitute what we call the atomic number. The proton and neutron constitute what we call the atomic mass or the average atomic weight. So we know that the atom consists of proton, neutron, electron. The proton and neutron forms the nucleus. Around the nucleus, you have the core electron. A maximum of 2 electrons occupy the space where the core electrons are found. The valence electron is the outermost shell. So the element is derived from the total number of proton. We combine the total number of proton and neutron to give the atomic mass. Isotopes are distinct number of species of the same element. Remember that the number of proton will determine the atomic number, and the number of proton and neutron will determine the atomic mass. So isotopes are different species of the same element. A molecule is basically a group of atoms joined together. The atoms can be joined chemically by covalent, ionic, or metallic bonds. A monomer is a molecule that can be bonded with another molecule to form a polymer. And from this, you can deduce that a polymer consists of a group of monomers joined together. Ions are atoms or molecules with a net electric charge due to a loss or gain of electron. A compound is basically 2 or more separate or different elements that are chemically bonded together. If you look at the image here, we have a monomer, and we already emphasized that the monomer is a molecule that can be bonded together, or a group of molecules that can be bonded together to produce a polymer. 2 monomers give you a dimer, 3 monomers give you a trimer, 4 monomers give you a tetramer, and basically eventually with polymerization you end up with a polymer. And you'll eventually see that you have different types of polymers that are responsible for producing compounds. We also mentioned the isotopes, and as we said, isotopes are different species of the same element. It just means that there are different numbers of neutrons that will affect what we call the atomic mass. So there's different number of neutrons that will contribute to the average atomic mass. We have different isotopes of hydrogen, such as protium, deuterium, tritium. The atom can be any element on the periodic table: carbon, hydrogen, oxygen. The molecule, 2 or more atoms joined together, 2 or more of the same atoms joined together, while the compound is basically a combination of molecules that are bonded together. So just a bit more focus on the periodic table. This is basically giving a bit more detail as to what to expect from each element. And we mentioned from the last lecture that you have 7 rows, which we call periods. Alkali metals, as we mentioned before: lithium, sodium, potassium, rubidium, cesium, francium. We also did mention that hydrogen is a non-metal, so it does not really belong to group 1. It does not belong to any group or class, actually. It's important to note that group 1 metals are positively charged ions. They are +1 charged ions, which means that they have 1 valent electron or 1 electron in their outermost shell. Group 2 metals, again, include beryllium, magnesium, calcium, strontium, barium, and these are 2+, metals, which means that they have two electrons in their outermost shell, or two valent electrons. We also did touch a bit on the transition metal. So the transition metals include scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, zinc. From the second row, we have yttrium, zirconium, niobium, molybdenum, technetium, ruthenium, rhodium, palladium, silver, cadmium. We also have lutetium, hafnium, tantalum, tungsten, rhenium, osmium, iridium, platinum, gold, mercury. This is the fourth block. So what we have: lawrencium, rutherfordium, rutherfordium, dubnium, seaborgium, borium, hassium, meitnerium, darmstadtium, rentigium. You also have the F block, which consists of the lanthanides, because its first element starts with lanthium, and the actinides because the first element starts with actinium. The lanthanides are cerium, praseodymium, neodymium, promethium, samarium, europium, gadolinium, terbium, dysprosium, holmium, erbium, thulium, euterbium. The actinides are named because actinium is the first element in that group. So these include actinium, thorium, protactinium, uranium, neptunium, plutonium, americium, curium, berkelium, californium, einsteinium, fermium, mendelevium, nobelium. So as we clearly outlined before, you have the alkali metals here, alkaline metals or alkaline earth metals, transition metals. Most of the periodic table is actually are comprised of metals. We have the halogens as well, as we mentioned in our last lecture, which include these here: fluorine, chlorine, bromine, iodine, astatine, tennessee. We also have the noble gases, which we mentioned in our last lecture as well: helium, neon, argon, krypton, xenon, radon, argneson. This basically shows the state of the atom at room temperature, which basically shows that the ions are actually solid at room temperature. Liquid at room temperature: bromine, mercury. Gases at room temperature includes all the noble gases as well: nitrogen, oxygen, chlorine exists as a gas at room temperature, as well as the noble gases that we mentioned: helium, neon, argon, krypton, xenon, radon. The artificially created metals include from our actinide, lanthanide series. It's important to note that these are highly radioactive metals. Just a little detail on the individual metals. Scandium is soft, shiny. It's a transition metal from Scandinavia. It is basically used in aluminum alloys for aerospace compounds. Titanium we know very well as well, and we also covered in the last lecture. Titanium has low density, it has high strength, it does not corrode easily. It is used for missiles and also for in aircrafts. Vanadium is used to make steel alloys. Chromium is used as protective coating on plumbing fixtures. Manganese is known from oxidizing agents such as potassium permanganate. Iron is basically everywhere from cutlery to the hemoglobin in your bloodstream. Coins as well. Cobalt is highly used in machineries and electronics. Nickel, we know, is found in alloys, batteries, and coins. Copper is found in wires, copper wires, electrical equipment, tubes, pipe. Zinc you find commonly used as sunscreen, cosmetics, and it can be used along with other metals, and it's also found in your body. Yttrium is found in aluminum and magnesium alloys. Zirconium is found in ceramics and it's also used to imitate diamond. So niobium can be used as semiconductors, and in alloys as well. Molybdenum is used to make steel alloys, lubricants, pigment. Technetium is a stable isotope that emits gamma rays for imaging. So for example, if you know of PET scan is basically imaging in the body where they actually use the isotope of technetium-99 to monitor the radio label glucose uptake. Ruthenium is used to coat electrodes. Rhodium is used in catalytic converters for cars. Palladium also is used for the same thing. Silver, we already know you use it to make jewelry, coins, mirrors. Cadmium used for rechargeable battery. Lutetium is used as a catalyst in the petrochemical industry. Hafnium resists corrosion. Hafnium resists corrosion and is used to make wires. Tantalum is used to make wires as well, and it is present in various alloys. Tungsten is used for heating filaments, electrodes, alloys. It has the highest tensile strength and melting point of all the electrons. Highest tensile strength and melting point of all electrons. Rhenium, osmium, they are both used as alloys. Iridium is used as a hardening agent for platinum, in which it's used in electrodes and jewelry. And of course, platinum is used in jewelry as well, electrode and other laboratory instruments. So for example, you have like the platinum loop that we use in bacteriology for urine culture. Gold, we already know is used to make jewelry. It is also present in various computer compounds. Mercury, we already know we use this in thermometers and barometers. And mercury and bromine are the only two. I might ask you this as a multiple choice question, naturally. At room temperature, which are the following elements exist in liquid state? Mercury and bromine. The other elements are highly radioactive, as you can see. These are not synthesized naturally. They are actually synthesized in particle accelerators. As much as these elements are man-made and are not commonly used, they're mostly used for scientific purposes. Uranium is basically used for nuclear reactors and also as weapons. This, along with plutonium, they're used in nuclear reactors as well as weapons. This is basically the chemical symbol. So the chemical symbol is designated N for nitrogen. The chemical name is nitrogen. The atomic number is 7, which means that it has 7 protons. The atomic mass is 14, which means that there is 7 protons and 7 neutrons. And remember that you can also have isotopes, which are species of the same element with different atomic mass. So the important thing about learning the elements of the periodic table is that you learn the composition of the human body. You learn the composition of basically almost everything that you see around. The human body consists of mostly of oxygen atom. 65% of your body consists of oxygen. So we know that the body consists of mostly water. 18.5% is carbon. 10% is hydrogen, followed by nitrogen. You have other elements such as calcium, phosphorus, potassium, sulfur, sodium, chloride, magnesium. You also have zinc as well as few others. These we call electrolytes in the body. For example, sodium, potassium, chloride. These ions exist in the intracellular and extracellular fluid to regularize various metabolic processes in the body. So as we mentioned, for all lectures, we'll try to give a little bit of attention to a few elements. Hydrogen, even though it's listed on the group 1 element, it's actually not a group 1 element. It does not belong to any group or class. It's a non-metal. Almost every molecule in your body contains hydrogen. It makes up 75% of the visible universe. It is the smallest and simplest element. It has 1 proton, 1 neutron, an average atomic mass of 1.0078. There are 3 naturally occurring isotopes of hydrogen, as we mentioned before. These include protium, deuterium, tritium. 99% of hydrogen exists in the form of isotope protium. Hydrogen is also diatomic, and you have different ways in which you can produce hydrogen. This can be done by reacting with metal and dilute acid, extreme forming of methane. It's also important to note that hydrogen is a very abundant element, hydrogen as well as helium. It is a fuel for nuclear fusion in the sun. We produce over 50 million tons of hydrogen yearly. And we use hydrogen for agricultural purposes, such as for fertilizers, for chemical pesticide production, for medical purposes, as well as for transportation. So you can also use hydrogen in the form of gas for energy production. So here is just basically emphasizing what we mentioned before. The atomic number of hydrogen is 1. The average atomic weight exists as a gas at 20 degrees or 68 degrees Fahrenheit. It is a non-metal that is hexagonal. I think they're trying to promote hydrogen as well for green energy, for wind, solar, or hydro. One of the ways in which you can produce hydrogen is by electrolysis, and it is used in nuclear reactions, can use for energy, it can be used as natural gas. A little bit more information on polymers. The word polymer is from the Greek origin. All polymers are made up of large molecules. As we already know, polymers are basically just a group of monomers. These are large molecules that are made up of smaller molecules linked end to end. So we know those are monomers. Polymers can be linear, branch, cross-linked, or it can be network. We use polymers almost every day. Polymers can be in the natural form, or it can also be synthetic. Natural polymers include cellulose, starch, protein, DNA, enzymes. Synthetic polymers include polypropylene, polyethylene, polyvinyl, polychloride, polyesters, polystyrene. If you look at the pictures above, we have high-density polyethylene. We also have polystyrene as well as polyvinyl chloride, and you will eventually realize that polymers are made up mostly of carbon atoms as well as hydrogen atoms. To create a different type of polymer, you basically can exchange different atoms to basically produce different types of polymer. For example, polyvinyl chloride is basically exchanging the hydrogen atom for a chloride atom. You have different types of polymers, and we know that polymers are a combination of monomers. Monomers are a combination of molecules. Molecules are a combination of atoms. So polymers include polyethylene, which we use every day, plastic bags, bottles, toys, electrical insulation. Polypropylene in our carpets, we have in bottles, luggages, exercise clothing. Polyvinyl chloride we have in bags for IV solution, tubings, floor coating. Polytetrafluoroethylene is used for non-stick coating and electrical insulation. This is basically just showing that the polymers are a combination of monomers. A typical polymer molecule might contain hundreds or even thousands of these small constituent molecules, which we call monomer, and the monomers are built up of assemblies of atoms. Polymer molecules are large. It is often helpful to think of them as a chain of monomers rather than a collection of atoms. Monomers, we already know, give you polymers, and we have different types of monomers, different types of polymers. For examples of monomers in your body would be a monosaccharide. An example of a polymer for a monosaccharide would be a polysaccharide, which is a carbohydrate. Fatty acid would be lipid. Nucleotide would be the nucleic acid, which include your DNA and your RNA. You can also call this polynucleotide. Another example of a monomer in your body would be the amino acid, which is the basic building block of proteins, and the protein would in this case be the polymer. From monomers to polymers, as we mentioned before, the plastic bottles in which your milk, juice, or shampoo came are usually made of plastic called polyethylene. Polyethylene molecules are composed entirely of just two elements, carbon and hydrogen. The carbon atoms are linked together in long chain that is called a polymer backbone of the polymer molecule, and there are two hydrogen atoms attached to each carbon. So basically, the polymers or the polyethylenes usually consist of a series of carbon atoms which are usually covalently bonded to each other. Hydrogen atoms are usually covalently bonded to each atom. So this is basically just showing the layout of polyethylene. This is the carbon backbone here. The black balls represent the carbon. The hydrogen atoms are represented with the white balls. The molecules are depicted with balls representing the atom. If one of the two hydrogen atoms on every carbon is replaced with a chloride atom, we will have polyvinyl chloride. The polymer is commonly referred to as PVC. Plastic pipe made from PVC have been widely used in plumbing. These are just examples of polyvinyl chloride. And if you replace one of the two hydrogen atoms, so for each carbon, you have two hydrogen atoms attached. This is basically showing that you can have repeated units of hydrogen chloride carbon that will have the extension of the polymer itself. We touched a bit already on the atomic structure and mass, but with my lectures, we'll have a lot of repetition because I do believe that repetition is necessary. Again, the atom is composed of a small compact core called nucleus that is surrounded by a dense core of electron. The nucleus is composed of two types of particles, the proton and the neutron. As we mentioned before in the last lecture, you have a lot of space between the nucleus and the electron. A better model of atomic structure views the electron as a cloud of negative charge, because as we said, the electron is negatively charged. A better view of the atomic structure views the electron as a cloud of negative charge that surrounds the nucleus, as opposed to particles that orbit it in an orderly way. As much as we imagine that the electrons are just particles orbiting the nucleus, it actually doesn't appear that way in reality. How they measure the electron is by different colors that are produced or wavelength that are produced. So the electron can appear at any location or at any point in time around the nucleus. Different photographic representation of where the electron is likely to be. So the number of proton and neutron provide a constraint on the electric charge. If you look at this periodic table that we have here, you can see the elements that are positively charged. These are +1 charge. As we said, the group 1 elements are positively charged or +1, and this means that they only have one electron on their outermost shell, called that valence electron. Group 2 or the alkaline earth metals are +2 charges. Most of the non-metals are actually negatively charged. The gases are neutral. The halogens are -1 charge. We have -2 charge and -3 charge, and we'll go into detail on these eventually. So the charges of ions and atoms are basically dependent on the numbers of proton and electron that are present. The International Systems of Unit of Charge is measured in coulomb. Every electron carries a charge of -1.602 times 10 to the 19 coulomb. Every proton carries a charge of +1.602 times 10 to the 19. So as we said before, the valence electron is an outermost shell electron of an atom that can form a chemical bond with another atom. The core electron usually admits only 2 electrons, a maximum of 2 electrons. The second shell usually admits up to 8, a maximum of 8 electrons, 2, 4, 6, 8, as you can see here. And the outermost shell usually can occupy a maximum of 8 as well, but the number of electrons on the outermost shell will basically determine the number of valence electrons. So the number of protons identifies the element. Carbon atoms make up the backbone of nearly all polymers, as we mentioned before. The atomic number of carbon is 6, which tells us that a neutral carbon atom has 6 protons. Electrical neutrality requires that a carbon atom also must have 6 electrons. So if it has 6 protons, because as we said, the number of protons determines the atom, the number of electron also has to be 6. This is the symbol of carbon, as we already know, and the atomic number is basically the number of protons, which is 6. The atomic mass is the number of proton and neutron, which is 12. Remember that we said that we also have different isotope of carbon, which means that you will have other carbon atoms with different number of neutrons. Another element that we will give a brief synopsis on is helium. It's basically the second element on the periodic table. So we actually looked at hydrogen. So helium is basically the second element with an atomic number of 2, which means that it has an average atomic mass of 4. Its physical state is in the form of gas. It also falls under the group of noble gases. Helium is the second most abundant element in the universe. When atoms are released in the atmosphere, they rise until they escape into space. Because helium has low density, when released in the atmosphere, it basically rises until it escapes into space. So it does not solidify at atmospheric pressure. It only exists on Earth's atmosphere only because it's constantly resupplied from different sources such as radioactive decay from the Earth's crust by volcanic activity or radioactive decay of uranium, thorium. You should also know of helium in the helium balloons or parachutes. We also have different isotopes of helium as well. Isotopes are atoms of the same element that have different number of neutrons. So because they have different number of neutrons and the proton is what makes the element, you can have different isotope of the same element. The atomic mass is also calculated based on the number of proton and neutrons. Then you can have different atomic mass of the same element. So protons and neutrons have similar masses. Each is nearly 2,000 times more massive than the electron. The mass of any atom is concentrated in its nucleus. So because the mass of the atom is concentrated in the nucleus, the mass of the atom will be entirely dependent on the number of proton and neutron. Not saying that the electron has no mass, but the mass of the electron is insignificant when you compare that to the mass of proton and neutron. This is basically just showing different isotopes of hydrogen, helium, lithium, carbon. The atomic mass is measured in atomic mass unit. Individual atoms are so small and light that reporting their mass is in conventional units such as kilograms or grams is not convenient. Instead, we use a unit that is appropriate to the atomic scale, the atomic mass unit, or AMU. One atomic mass unit is equivalent to 1.6605 times 10 to the minus 24 grams. And it's basically the same thing here. So how many atomic mass unit in 27 grams of mercury? 27 grams of mercury times 1 atomic mass unit divide by 1.66 times 10 to the minus 24 grams of mercury is 1.63 times 10 to the 25 atomic mass unit per mercury. Both the neutron and protons have mass very close to 1 atomic mass unit. So the neutron itself has an atomic mass of 1.009 atomic mass unit. The proton almost measures the same. Proton is 1.007 atomic mass unit. And as we mentioned before, the electron is almost insignificant when it comes to mass when compared to the proton and the neutron. The electron is basically 0.00055 atomic mass unit. We can determine the mass of an atom simply by counting the number of proton and neutrons, because as we said before, if 1 proton is equivalent to 1.007 atomic mass unit, if you have 7 proton, then you already know that is 7 times 1.007 atomic mass unit. So we combine the total of protons and neutrons and it's called the mass number. So if you want to know the mass number, then you'd have to add the total expected number from 1 neutron to the proton. Because isotopes are atoms of the same element with different number of neutrons, they will have the same atomic number, but they'll have different atomic mass. The first important function of a mass spectrometer is to take a stream of microscopic particles, for example, the atom or molecule, and sort them according to their mass. This is how we actually started discovering isotope with a spectrophotometer. So basically, they expose, once the particles have been separated by mass, second key function of the mass spectrometer is to measure accurately the number of particles within a given mass. Then we also have the atomic symbol. E represents the atomic symbol for the element, A is the mass number, Z is the atomic number. So again, the atomic mass is defined as the average mass of an atom of a particular element. It is the smallest quantity of matter that can be weighed in about nanogram or 10 to the minus 9 gram. A nanogram of carbon would contain more than 10 to the 13 atom. And this is basically just showing again the atomic number, the atomic symbol of carbon, as well as the relative atomic mass. Smaller number is always the atomic number. A larger number is always the average atomic mass. So how do we calculate the atomic mass? Multiply the mass by the fractional abundance to weight, each isotope's contribution to the atomic mass. Of 99% of the carbons comes in carbon-6, which means that the average carbon will have an atomic mass of 12. However, there are different isotopes of the same thing, which means that there are other carbon with more than 6 neutrons. For example, you have carbon 13. Carbon 12 would be 12 times the 98, 0.983, which is the 98% of carbon 12 that is available, and this will basically give an average of 11.87. Carbon 13 exists in an abundance of 0.017, and the average mass is derived from the relative abundance of carbon 12 as well as carbon 13, which would give the average atomic mass. So this is basically how they derive the average atomic mass, by giving the average weight of all isotopes that exist. The value of 12.011 found in the periodic table is obtained using additional significant figures on the isotopic abundance number. When the number of protons and the number of electrons do not match, the result is a species with a net charge called an ion. Such species are no longer atoms, and their behavior is markedly different from that of atoms. Ions can be positively charged or negatively charged, and we call these cation or anions. Most of the elements are group 1 and group 2 elements. We already know our group 1 and group 2 elements are positively charged ions, and these include, we already mentioned before, hydrogen, sodium, potassium, rubidium, cesium, in addition to other transition metal elements and a few non-metal. We have the negatively charged ions or anions. These include the noble gases such as chlorine, fluorine, chlorine, bromine, iodine, astatine. We actually mentioned them before, as well as a few other compounds. And this is a basic representation of our group 1 and group 2 metals or elements, group 1 and group 2 elements, which we mentioned just now. These are positively charged cations from group 1. Group 1 plus charge, these are 2 plus positively charged cation as well. We also mentioned a few examples of transition metals, for example, mercury, cadmium, zinc, gold, iron. Halogens are negatively charged anions include fluorine, chlorine, bromine, iodine, astatine. And we also have oxygen, silicon, nitrogen, among others. So we know that charged ions can exist in the form of anions or cations. When an ion is derived from a single atom, it's called monoatomic ion. When groups of atoms carry a charge, they are called polyatomic ions. Negatively charged ions are called anions, and ions with more protons than electrons have a positive charge and is called a cation. These are examples of monoatomic ions. These include, as we said, the group 1 elements, as well as some of the transition metals. Monoatomic anions have names ending with "ide." Cations simply have ions added to the name of the element. Monoatomic ions include fluoride, sulfide, nitride, and we also have the cation, which we said have ion added to the name of the element. So the cation, which are the elements in group 1, 2, sodium ion, lithium ion, potassium ion, magnesium ion. The mathematical description of ion basically look at the charges or what makes an ion. So the general principle is like charges repel, unlike charges attract. Q1 and Q2 are charges. E is north, is a constant called permittivity of a vacuum. R is a distance between the charges. So this is basically looking at the force between the atoms. So F is the force the object exerts on another as a result of their charges. Looking at this expression, when both charges have the same sign, either positive or negative, the resultant value for force is a positive number. Sodium atom lose an electron relatively easy to form a sodium cation. When we have an anion and a cation together, we end up with an ionic bond. It has high melting point. Yes, it's soluble in water. It's a good conductor when melted or dissolved. Covalent bond is a chemical bond between two non-metals. So for example, we have two gases, hydrogen and oxygen would produce covalent bonds. They are good insulators. Metallic bonds are good conductors of electricity as well as heat. And an example of metallic bond would be ion binding to another ion. A chemical compound is a pure substance made up of atoms, two or more elements joined together by chemical compounds. In many compounds, atoms combine to form discrete particles called molecules. Chemical formula describe the compound in terms of the constituent of element. The chemical formulas is basically trying to give an idea or a clear description as to the amount of atoms that is present, the type, and the amount of element. So for example, the molecular formula of ethane means that there is 2 carbon as well as 6 hydrogen atom. Molecular formula for ethanol is C2H6O, which means that there are 2 carbon, 6 hydrogen, and 1 oxygen. Propane, C3H8, which means that 8 hydrogen atoms, 3 carbon atoms, and these are the structural formula: 2 carbon, 6 hydrogen, 2 carbon, 6 hydrogen, 1 oxygen, 3 carbons, 8 hydrogen, and these are the condensed structural formula. There are 2 distinct types of chemical formulas: molecular formulas and empirical formulas. The molecular formula gives the number and types of atoms. For example, molecular formula of ethylene monomer, from which polyethylene is produced, is C2H4, which means that there is 2 carbon and 4 hydrogen per molecule. The empirical formula basically gives a relative ratio between the numbers of atoms of different elements, a more simplified and a shortened version of the formula. So let's consider ethylene again. The ratio of carbon atoms to hydrogen is 1:2, so the empirical formula is CH2. For ethylene, this would give us CH2, and it's the end just basically means that it's an extension or repeating unit of CH2. We have different compounds. Hydrogen peroxide, the molecular formula for hydrogen peroxide is 2 hydrogen atoms, 2 oxygen atoms, and definitely the simplified version of this is is HO, or the empirical formula. For water, we already know it's H2O. We don't oversimplify it because it's already simplified. Glucose is C6H12O6. How to simplify this? We divide all of these by 6. 6 divided by 6 is 1. You basically don't write 1 in the empirical formula. As you can see, you basically don't write 1. 6 divided by 12 is 2, so we end up with 2 hydrogen, and 6 divided by 6 again is 1, and because we don't write the 1, we end up with a CH2O. For ethanol, C2H6O. The easiest way to simplify this would be C2CH2O. But naturally, if we simplify this way, we end up with a CH2O, right? The simplified version has to remain like this. For ethane, we have 2 carbon, 6 hydrogen. We divide this by 2, we get CA3. Ethylene, we have 2 carbon, 4 hydrogen. We divide this by 2, we get CH2. And lastly, we have caffeine, C8H10N4O2. Easiest factor would be to divide this by 2. This will give us 2 divided by 8. So this is 2. 10 divided by 2, as well as 4 divided by 2. Naturally, 2 will divide by 2. We end up with C4H5N2O. We mentioned a bit about polymers before, as well as PVC, polyvinyl chloride, and we also mentioned that if you replace one of the hydrogen atoms or the second hydrogen atom, you basically get polyvinyl chloride. Polyvinyl chloride is used for plastic pipe tubes and a lot of different synthetic products. Several different types of chemical bonds are possible. First, all bonds include exchange or sharing of electron. So it's either exchange the outer electron or you share the electron. The exchange or sharing of electron result in the lower energy for the compound relative to the separate atom. So when we have opposite charges coming together, we form ionic bond. So for example, group 1 elements that are +1 positive charge, halogens, which are the group 17 elements that are negatively charged, they can form ionic bonds. For example, sodium, we know, is a group 1 element. Sodium is a positively charged cation. Chloride is a negatively charged anion. These can come together to form ionic bond. When electrons are shared between pairs of atoms rather than donated from one atom to another or mobile across an entire lattice, we call that a covalent bond. So the electrons are shared, they are not donated. And this is usually between 2 non-metals. In covalent bonds, electrons are usually shared in pairs. So it can be 2, can be 4, can be 6. Hydrogen and oxygen form a single covalent bond to give you a water molecule. Carbon and oxygen covalently bonded together, they share 4 electrons to form carbon dioxide. And then you have the triple bonds, which basically means that they share up to 6 electrons. For example, a nitrogen bond. So it's important to note that the long chains in all polymers, as we mentioned before, are formed by covalent bonds in which electrons are shared between the adjacent carbons. The backbone of polymer usually consists of carbon, and most polymers consist of carbon, hydrogen atoms. Smaller, more familiar molecules such as water, carbon dioxide, and propane are simpler examples. And the bonds that hold monomers together, as well as bonds between atoms within each monomer unit, are also covalent bonds. Covalent bonds hold atoms together. Covalent bonds hold monomers together in order to give you polymers. The bond type between hydrogen and oxygen or water is basically a polar covalent bond. The bond of methane, which is carbon and hydrogen, is a non-polar covalent bond. The bond between oxygen and carbon to give you carbon dioxide is a polar covalent bond. Ionic bond, as we've said before, there is a sharing of electron. In this case, sodium atom will form an ionic bond with chloride, where you actually have a loss of electron for sodium electron to produce a sodium chloride ion. So in that case, the chloride will gain an electron while the sodium atom will lose an electron. A sodium atom loses one electron to an electron acceptor and form a sodium ion, and chloride atom accept one electron from an electron donor to become a chloride ion. This is also defining ionic bonds is a chemical bond that forms when valence electron or electrons is completely transferred between atom, and bonds generate two oppositely charged ions. So in this case, you have lithium that loses an electron, fluorine gains an electron. So ionic bond is basically between a metal, is usually between a metal and a non-metal. And as we've said before, the group 1 metals, which are positively charged ion, and the group 17 non-metals we know as halogens, they tend to form ionic bonds with elements from group 1 easily. Lithium, as we already know, is a group 1. Fluorine is a group 17 non-metal. This lithium cation will merge or integrate with fluorine anion to basically give a lithium fluoride molecule. And again, we know that the sodium loses an electron while chlorine gains the electron to form a sodium chloride molecule. The sodium and chloride ions are attracted because of their opposite charges and are held together by an ionic bond to form a molecule of sodium chloride. In metals, the atoms are once arranged in a lattice, but positively and negatively charged species do not alternate. This is not like we see in ionic bond where there is a positive and a negative charge. In metallic bond, instead, the nuclei and some fraction of their electron comprise a positively charged core. The nucleus that is positively charged localize these lattice points, and electrons move more or less freely through the whole array. This is called metallic bonding. So basically, nuclei of the metallic elements are closely arranged so that the electrons form a lattice. The bonding tend to occur between the lattice that is formed. So metallic bonding occur when a group of metals share a cloud of valence electrons. So this is also just a simple representation of metallic bonding. In this simple conceptual picture of metallic bonding, each metal atom contributes one or more electron to a mobile electron C. So basically, the lattice or this electron C is basically mobile, so the electrons actually move freely. The ability of the electrons to move freely through the C allow the metal to conduct electricity. Here, the blue area depicts those mobile or delocalized electron, and the red circle represents the positively charged core of the individual atoms. In the metallic bonds, the nucleus and the inner electron provide a positively charged core. The outer electron form a sea of negatively charged surrounding the positive core. So it basically forms a lattice of electron where the electrons can move freely, and that is the basis of metallic bonding. Just a synopsis, the horizontal rows are called period. Remember that we said that you have 7 rows. The vertical columns are called groups, and we also know that you have 18 groups. Group 1 elements are usually +1 charge, and they tend to form ionic bonds between group 17 elements. The transition metals are located here. Ion is an example of transition metal. The element that appears below the rest of the periodic table we know are called lanthanides and actinides. Because I understand that with speaking, it's difficult to form permanent memory from just listening to the information. You're assisted by reading as well, but I try to repeat the information in different ways because I know that this information is a bit intricate. It will take a lot of repetition for you to form permanent memory, especially with the details of the periodic table and all. Just be a little patient and hopefully you'll be able to retain much of the important stuff. As we already know, the periodic table can be divided into metals, metalloids, non-metals. But we're fully aware of the metals, and as I said before, most of the elements on the periodic table are actually metals. Small amount are non-metals, and these are designated here. The rest are non-metal. Covalent bond occur when they are both non-metals. Ionic bonds occur between metal and non-metal, and metallic bond is basically between metal. So most of the elements are metal. So the metals are located to the left of the periodic table. Metals share a number of similarities in chemical and physical properties. Physically, metals are shiny, malleable, ductile, meaning that they can be pulled into wires. They also conduct electricity. So wires are always made from metals. Chemical properties can also be used to distinguish metals. The non-metals, as we've said before, they occupy the right-hand portion of the periodic table. There are fewer non-metals than metals, as we can see, and most of the molecules that make up the human body consist predominantly or exclusively of non-metallic elements. Your carbon, your hydrogen, your oxygen, your nitrogen, your sulfur, your phosphorus. So basically, most of your body is made up of non-metal, to no surprise. And most of the polymers are also made of non-metal. So polymers also consist exclusively of non-metallic elements. In contrast to metals, non-metals are not shiny, not malleable or ductile, nor are they good conductors of electricity. So the non-metal, for example, these are polymers, and we already know that the backbone of most polymers are made up of carbon, polyethylene, polyvinyl chloride, polypropylene. All of these polymers, synthetic polymers, as well as even natural polymers, tend to be made up of carbon. The metalloids or semi-metals include boron, silicon, germanium, arsenic, tellurium. The study of chemistry is broken down into either organic or inorganic. Two of the most fundamental areas of chemistry are organic and inorganic chemistry. A more modern definition is that organic chemistry is the study of compounds of elements, carbon. So organic chemistry tend to be centered around focusing on the study of carbon. So I guess that would include a lot of the polymers and the synthetic materials that we produce. Inorganic chemistry is the study of all other elements and their compounds. One such compound is silicon tetrachloride, and this has an important use in the production of semiconductor. So organic chemistry looks primarily at the study of carbon atoms, while inorganic chemistry looks at all the other atoms and compounds and their compounds. 4 chloride atoms surround a central silicon atom, and each chloride share one pair of electrons with silicon. These are examples of organic compounds and inorganic compounds. Proteins, carbohydrate, alcohol, chloroform, these are all organic compounds. And as we've said before, organic chemistry tend to focus on carbon. As we can see here, silica, marble, bauxite, ammonia, these are all inorganic compounds. Silicon and chloride are both main group elements found in group 14 and 17 of the periodic table. Sodium is group 1, chloride is in group 17, so we can expect that other pairs of elements from these columns of the table will form ionic solids too. Compounds such as lithium chloride, sodium fluoride, potassium bromate have structures analogs to that of sodium chloride. Group 1 form cations with +1 charge, and all of the elements in group 17 form anions with a negative charge. Any of these can combine with any of the anions in a 1-to-1 ratio to form a neutral compound. And here here we have the group 1 elements, and as we've emphasized before, these are +1 charge, these are +2 charges, these have no charges, are minus charges, -2 charge, -3 charge, +3 charge for aluminum. And there are other transition metals with different charges that can also be combined. So with the study of organic chemistry, it's important to note that all organic compounds feature carbon skeleton. Other elements frequently found in organic compounds include hydrogen, as we mentioned before, oxygen, nitrogen. More than 18 million organic compounds exist. Carbon atoms are readily attached to one another to form chains, and these chains can grow quite long. So this is basically showing methane, ethane, and propane. These are all carbon and hydrogen atoms. Methane is 1 hydrogen atoms, ethane 2 carbon, 6 hydrogen atoms, propane 3 carbon, hydrogen atoms. It is not uncommon for several different organic compounds to have the same molecular formula. Different compounds with same molecular formula are called isomers. Different molecular compounds with the same molecular formula are called isomers. And this is basically giving a little synopsis here on what isomers are. Isomers are molecules have the same molecular formula but different structures or arrangement of atom in space. This phenomenon is called isomerism. As in any structural formula, lines are used to depict bonds between atoms. The line formula is also another way of depicting atoms, especially in organic chemistry or for polymers. As in any structural formula, lines are used to depict bonds between atoms. But in a line drawing, many of the elemental symbols are omitted. By definition, an organic compound is based on carbon atoms. So if you already know that it is an organic compound, then you know that the backbone is going to be carbon. So in this case, sometimes you will see that the carbon backbone is omitted in a lot of cases in the line formula. So to reduce clutter in the line drawing, the C symbol of carbon is not written. And as you can see here, we have different organic compound, the ethanol C2H6O. Here we can actually see that all the carbon and the hydrogen are removed. So you can actually basically just fill in the blank. The oxygen molecule, oxygen atom is actually not omitted in this case. You have isobutyl here, similar expression, octane as well. This is basically the 3D representation or the 2D two-dimensional structure or the Lewis structure, and this is basically the line drawing where the carbon, naturally you would expect that the carbon atom would be here, hydrogen would be here as well as here. Symbols are written for any element other than carbon and hydrogen. So that's important to know that if for a line drawing, the hydrogen and the carbon is usually not represented, as you can see. And for a line drawing, by removing the symbols for all carbon atoms and for hydrogen atoms attached directly to carbon. Carbon atoms remain, so carbon atom position become either intersection between lines or end of lines. Bonds between carbon and hydrogens are also omitted. So methane, ethane, ethylene, benzene, we can see that these are hydrocarbons. We see that they're natural hydrocarbons in that they consist only of carbon and hydrogen atoms. Methane, 1 carbon atom, 4 hydrogen atoms. Ethane, 2 carbon atoms, 6 hydrogen atoms. Ethylene, 2 carbon atoms, covalently bonded to 2 carbon atoms, 4 hydrogen. Benzene, 6 and 6. So these are structural formula as well as a stick model representation of each. When 2 non-metal combine, they usually form a covalent compound. metal and non-metals combine with one another, and we already know that this forms an ionic compound. So ionic compounds include sodium and chloride, potassium iodide, calcium sulfide, magnesium oxide. A given pair of elements can form compounds in a number of different ways. Nitrogen and oxygen, for example, they form nitrous oxide. They can come in different forms such as NO, N2O, NO2, N2O3, N2O4, N2O5. NO is nitrogen monoxide, N2O dinitrogen oxide, NO2 nitrogen dioxide, N2O3 dinitrogen trioxide, N2O4 nitrogen tetroxide, N2O5 nitrogen pentoxide. In a binary compound, the element that appears first in the formula also appears first in the name. The element that appears first is basically the name that will appear first. The first element retains its full name, whereas the second element is described by replacing the ending from its name with the suffix "ide." Both elements will be preceded by a number of designating prefix, except that when there is only one atom of the first element, it does not carry the prefix mono. Polyethylene can be found in items ranging from plastic grocery bags to children toys, automobile gas tanks, and even bulletproof vests. Monomers called ethylene and of polyethylene are called ethylene. Formula of ethylene is C2H4. Polyethylene can vary in density, can be low density, can be ultra low density, can be high density polyethylene. This looser packing of molecule produce a plastic with a much lower density. So because the molecules are loosely packed together, you produce a lower density. Branch polyethylene is usually referred to as low density polyethylene. So these are low density here, polyethylene. Commonly used in application where as relatively little strength is needed, such as plastic films, sandwich bags, and squeeze bottle. High density polyethylene is also known as linear polyethylene. It is a strong and hard material used in bottles, kitchenware, as well as structural plastic in many children toys. Because their chains cannot be stretched out straight, branch polyethylene molecules cannot be packed together so closely as those of the linear polyethylene. Polymerization technology have made it possible to grow extremely long linear polyethylene chains stretching to hundreds of thousands of monomer units. Because the individual molecules are relatively large and heavy, this is called ultra-high molecular weight polyethylene, or UHMWPE. And here we have example of ultra high molecular weight polyethylene. Just a brief synopsis. You guys should commit to memory the definition of an atom, as well as a molecule, a monomer, polymer, isomers. You should also know the distinction between the different types of bonds, covalent, ionic, metallic bonds. Also, the different groups in the periodic table, or the different periods in the periodic table. Know at least 2 elements from each group or example. Have an idea as to what combination could give you an ionic bond versus a covalent bond. Friends with a molecular formula, empirical formula, or a line representation of polymers. Guys, if you have any questions, feel free to ask in the comment section. You can also email as well as WhatsApp, and I'll see you for the next lecture.